Hey, this is the long review of the paper Wav2Seq by ASAP Inc., CMU, and the Cornell University. Starting from the beginning, what do they do? As we all know that you can check the videos I made on the Wav2Seq 2.0 and Hubert. I have all of them. You can know that the training targets in the Wav2Seq are quantized vectors. Because of the quantized vectors, it's in the continuous space. So this is why they're using contrastive loss. Right? When regarding the Hubert, it's developed after the Wav2Seq 2.0. The authors simplify the training by saying, okay, I can first extract my capture features like the filter bank or MFCC. Then I could cluster those MFCCs in the feature space. Okay. Then I call each cluster something called the audio units. I call it audio units. Okay. They assign ID to it. So when they assign the ID to it, they regard this as some sort of a pseudo audio unit ID. So this time they have discretized the target, right? So this is why regarding loss, Hubert is using cross entropy loss. Okay. Regarding Wav2Seq, this paper, and you can see the authors say they're also doing this pre-training model. It's still pre-trained on audio, okay? But they moved one step forward. Instead of using the pseudo audio IDs, they propose something called the pseudo subword IDs. And you can see that by doing this, they claim that they were able to introduce the notion of language into the pre-training model. So, aka the pre-training model learn more about the spoken language. This is they claim why their pre-training model it needs less amount of transcribed data for fine-tuning the second stage decoder training. For instance, CTC loss-based decoder, transformer decoder, it all needs less amount of data to achieve the same performance if you use their Wav2Seq pre-trained model. Okay. All right. Let's see what their algorithm is. We'll skip the introduction. They have a very good introduction, to be frankly speaking. And if you saw the models they mentioned in their introduction, I don't know what is it about. You can search the keyword in my YouTube channel. It's called Wave Unit. Most of the time you will find a tutorial video or paper reading on the method they're talking about. Okay. And I would give you a quick review of the equation 1. So they first talk about the idea of a pseudo ASR, okay? And they talk about sequence-to-sequence ASR. So what is sequence-to-sequence? It's very simple. Suppose you have a sequence-to-sequence model. All it does is when you have a audio input X, and the sequence-to-sequence model converted into a sequence of Y. and X is in the more like in the continuous in the time domain. Okay, sorry. So it goes from x1 to x capital T, but y is in the word piece or word domain, right? Discretized domain. So it only has n outputs, not t output. Okay, and what does this loss is about? They're calling this a negative log likelihood. I think it's cross entropy loss. I will give beginners a quick review of what this is about. Okay. The first, for the ordered pairs in the training set, okay, x and y belongs to the train. Yeah. And that you want to maximize what? The posterior probability, right? Y given x. And because you're using a loss, you can write this into, I do not copy this, okay? Just put it here. Yi given x, right? I think it's not like this. Let me open a new page for you, okay? I think I'm running out of space here. But this is a tutorial on the cross entropy loss for ASR. So it's okay. It's first of all, they're trying to minimize this. X and the Y belongs to train. Okay. And this is Y given X. You want to maximize, always want to maximize the posterior probability, not the conditional probability. You're not doing the generative model, you're doing the discriminative model, okay? They add a log here. You will see why they're using log here. And this, I would just call this as this, okay? This represents this. So I don't have to write this. And then they made a, usually in the ASR, it uses a auto-regressive decoder. You can call it classifier if you want, but we always call that decoder. Why is it called decoder? Because it's sequential, using the sequential data. So classifier is only for one label or two label, right? Decoder is for one sequence. So usually called AR decoder. So the biggest assumption the AI decoder made is at the time t, the output y is only dependent on all the input x and all the y histories. It can be yt minus 1, yt minus 2, and y1. Okay. So you say y is not dependent on t yt plus 1. Pause the video and think about 10 seconds. Because ASR is monotonic. Why? Because you can see while I'm speaking, what the next word I'm going to utter is mostly dependent on the previous words I have spoken. For example, I say, I want to go to, the next word could be school, office, railway station. It does not depend on the future words. For instance, I want to go to school because it has something I want to learn. So the because is not dependent. So the school is not dependent on the because, but dependent on I want to go to, right? That's the assumption. And people have, researchers have been doing experiment and demonstrate that the speech has, I think I want to change this. They demonstrate that the speech has this beautiful characteristic, which is monotonic. But the language, it does not. So when you do the machine translation, for instance, the orders may change. For example, in English, it's red apple, right? In Spanish, they call apple red, or rojo. Yeah. You see the order has been altered. Okay. So when we remember the monotonic assumption, or it holds, the assumption holds. So we can write this into yn minus 1, blah, 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 y1 given x, right? Times p yn minus 1, y1 given x, until I reach to the first y. You got this, right? And because we're doing this log multiplication is equivalent to the summation of log, right? And the sum of the term it can be written is sum over n. Any question about this? No. And in each term, is this, right? This. So this is how the equation 1 comes. Okay. And then the author said, okay, they want to introduce something called the pseudo language. I think their writings need to be improved. Gonna just go to the figure and let you see everything here. For those of you who have not checked my tutorial video or paper reading video on Hilbert, please check the video, okay? I have a video on this. And you can see this is audio input, and it passes through a pre-trained model. For example, the Hilbert model. It contains probably several blocks of a transformer encoder layers, okay? And they come up with a hidden feature vector. Sometimes people call that contextual vector. That's fine. And when we have these vectors, remember in the Hilbert, what do people do? Right. In Hilbert, they do the same thing. They use the k-means to cluster these vectors into clusters. And they come up with this cluster indices. Up to this stage, it is exactly the same as Hilbert, but starting from here and to the top, it's different. Let's see how. So in the Wav2 sequence, the first thing they did was they view these IDs as characters. And I think in their writing, usually they have 500 cluster IDs. So you can imagine that they developed a pseudo language, and that language has 500 pseudo characters. You may say, okay, wait, which language has 500 characters? English definitely has way less than this. I think English has 50 at most. Even you include those punctuations. But for Mandarin, it definitely has more than 500. I think it has about 5,000, or at least 3,000. Okay. Anyhow, they come up with these pseudo characters, and then they run another stage called a deduplication. What is that about? Because you can see that here, because it's likely that when you're speaking an utterance from frame to frame, I mean, every 0.1 second or 0.05 seconds, the cluster ID does not change, and so the pseudo character do not change too. And this is why you will have consecutive identical pseudo characters. What they were doing is that they're doing something similar in the CDC decoding. Okay, they're squeezing or removed the redundant pseudo characters. So in short word, they only keep the one pseudo character if many appeared. So they come out with the KTV SHXOD. Okay, this is easy to understand, right? And the next step, they're using something we all know. Remember in the BERT model, you have this type of byte pair encoding. Sentence piece, same thing, right? You can think about how people train the BPEs, okay? But this is the same thing. So for each audio input, they come up with a sequence representation in characters of this audio. So it's very natural for them to use the BPE to decide or to come up with the subword. BPE is always, come up with from I think BPE is always from the letter to word piece, right? Yeah, I think the word piece, subword, they are same thing to me. Usually NLP people like to use this. Subword, usually this concept come from the speech. It represent or something related with the pronunciation. But nowadays, subword, people also use this. You can think these two are equivalent. And the character letters, I think English doesn't have characters, okay? But when you say these are pseudo characters, you can say, okay, letter or pseudo character, they are in the same concept, right? So this is why they come up with the pseudo subwords by running BPE encoding, a BPE on the pseudo character sequence or all the sequence in the training set. Okay. I hope this is clear to you. And you can ask, you may ask, wait, what do they do after they come up with the pseudo subwords? Pause the video for 10 seconds. Okay. After they get this, they can train using the CE laws for sure. But what they can do different than the Hilbert pre-trained model, which just use the vanilla CE, which does not take the sequence information into consideration. Well, in their paper, they can use the sequential based CE laws in their model training. Is that clear? So you may ask why I want to go with the sequential based CE laws. The benefit of the sequence based CE laws is it do not just optimize on certain frame or certain segment. It optimizes based on the whole utterance, right? So you remember previously it just optimized on this frame, and they sum up all the losses on each frame. And you can see that it's very likely you end up with some local optima. But when you consider this sentence, which has 100 frames, for example, put that into a sequential based CE loss, then you optimize the target as a whole utterance. Yeah, you don't end up with a local optimum. Okay. So remember, for speech, sequence is important. Yeah, speech sequence. Okay, I think I ended up explaining the algorithm. Now I'm gonna check the results. On table 1, they compared, first of all, a baseline with a CTC loss. They mean the decoder is being trained using CTC loss. With only 10 hours of LibreSpeech data. Okay. Oh, they pre-trained on the LibreSpeech only. I think they should pre-train the model on some bigger model, because I think it only makes sense to pre-train on a very large amounts of data. And you can see, definitely for CTC training, having more encoder can reduce the WER. Having more layers in the encoder is important. And this is baseline. Okay, now you can see what is sequence-to-sequence model. Yeah, like I mentioned, sequence-to-sequence model, you can see this is more like a transformer without self-attention. You can understand it like this way. You can say also say, okay, wait, why transformer is not sequence-to-sequence model? Of course, transformer is also in the concept of sequence-to-sequence, but the sequence-to-sequence mentioned in author's paper is transformer without self-attention. And you can see the Hilbert model is not even close compared to CDC. This is why CDC model, it has less sophisticated architecture in decoder compared to sequence-to-sequence, so it's easier to train. Need less amount of data, only 10 hours of data, they can come up with something that's meaningful, okay? And then they move on to the Wav2 sequence. And you can see that instantly the WER dropped a lot, but it's still worse than CTC, and they are trying to increase the numbers of layers in the encoder and reduce the number of layers in the decoder, which they say, okay, they want the encoder to learn more about the knowledge so they can reduce the amount of the data that's being needed in training the decoder, right? So they come up with a better number. That's still slightly worse than CDC. And they finally, I think this is not a fair comparison, okay? They are using a pre-trained model from Hilbert. That means that this encoder is different than this encoder, right? And they come up with better results. Yeah, that's okay. And then they compare the models called transducer. Transducer. I saw they point out the transducer to Alex Graves' RNT paper. So they're talking about RNT. Yeah, you can search in my channel. I'm not sure whether I will gonna do a tutorial on RNT because it's very general. But if lots of people are requested, I will make a tutorial on this. The difference of the RNT to transformer or sequence-to-sequence model, of course, RNT is also in the concept of a sequence-to-sequence. Okay. But I think the RNT, the issue is that so usually the RNT we're talking about is RNT decoder, right? It is, you can see RNT is a recursive, so it is an autoregressive decoder. So conceptually speaking, it's going to be better than the CTC because CTC has a very strong assumption, which is the conditional independence assumption, right? It assumes that the future and the past are not relevant given the current input. But RNT assumes that, okay, so my yn is always dependent on y1 to yn minus 1. Okay. So this is assumption. But the issue of the RNT is that it does not look into the future. So it assumes that the current is not dependent on the future. But sometimes for speech recognition, you need to look ahead a little bit to get better recognition accuracy. So the sequence doesn't make the strong assumption of the current that do not depend on the future. So you look ahead a little bit. So I think this is the reason why sequence or transformer looks at everything, right? Self-attached looks at everything. So why is why the transformer is better than RNT? Especially you see the transformer encoder. A transformer encoder spans over the whole utterance, okay? But the RNT is not. I think this is the reason why RNT is behind the performance of transformer. But RNT is not, I think it's not comparable to sequence. They are different in many ways. So I think it makes sense that the RNT is getting worse results than the CTC and the sequence because RNT needs lots of data to train. It takes a lot of time. And the 10 hours of data is not enough to train the RNT model for sure. Okay, then they also compare the transformer S to T. Okay. They finally compare the transformer model or transformer decoder. S to T, they mean transformer decoder. It's also AR decoder, right? But the encoder looks at everything. It's supposed to get the best results. Okay. But it's not. Why? You can see for 10 hours of data, the STT was not even close at all. And for only 100 hours of data, STT can achieve roughly the same performance as CTC with 10 hours, which is 36.5. This one is 32.8. Also, transformer decoder needs a lot to transcribe the data to be trained too. And the authors, they applied their pre-trained model with the transformer model, okay, which is that they replaced the transformer encoder with their pre-trained model, okay. So the architecture is like this. So traditionally, the transformer is like an encoder, and this is the decoder. This is the cross attention, yeah, and this is the YT. Sorry, no, it's not YT. Sorry, YI. And this is a loop back to the here. Yeah. So this is AR coder, right? So this is the traditional transformer. This is the inputs. Okay. And then in there, what they were doing is that instead of training a encoder from scratches, as the traditional transformer model does, they replace their encoder model with their Wav2Seq pre-trained model. It's also encoder, okay? And they say, because this encoder, although they're using some unsupervised data to train this encoder somehow learns something about the language, the speech, the audio, the contextual information, and something called that they claim called the pseudo language, pseudo subwords, things like this. It serves as a better encoder model, gets better embedding output at the encoder level, so it reduces the effort that's being needed in the training of the decoder. And this is why it's significantly better than the baseline transformer model. Okay. They also compared more training results. I think my understanding is this is talking about the same thing, right? But they only test on the dev other and test other on the libre speech. Yeah. But I think the author would be having more convincing results if they first train or pre-train the baseline on the LibriVox 60K hours of untranscribed speech. First pre-train on this, and then they try their Wav2 sequence pre-train on this, and then they use the full 960 hours of a Libri speech, transcribe the data, to update their decoder. Okay. And then the results would be more convincing to me. Looking forward to this. And they also compare the spoken name entity recognition. The result is better, but to be frankly speaking, I didn't see in-depth analysis why this is working. I understand this could be better for the ASR, but why this thing can be good for the NER in ASR? And they also run the results on experiments on speech to text translation. But I'm fairly new to this, so I know they're getting better results, but I'm gonna skip review of this because something are new to me. For instance, MBART, I don't know what's that, and I know the blue score, but machine translation, I probably is like most of you, so I wouldn't comment on the machine translation results. Okay. They did some ablation study, which I am a big fan of. So let's take a look at their comparison. First of all, they want to see what's the proper vocabulary size. First of all, we want to decide how many clusters of they should use to cluster these encoders output, right? Come up with the 25, 100, and 500. 25 is like English, right? And you can see on each block, the first row, you can see 100 is best. If you just say, okay, oh, they changed the BPE. Yeah, they should do better on this. Okay, let's take a look at, okay, suppose they fix the number of clusters. Okay, they want to see, but definitely in the BPE, you can control the vocabulary size for sure. When you're having bigger vocabulary size, that means the subword will have a shorter length, right? But if you have smaller vocabulary size, that means you have longer subwords or word pieces. And you can see in this case, 1,000 is the best. And then you can see on average, so a sentence will be compressed by 10 times. Okay, let's give you a rough idea of what is how much they compress the audio inputs into textual or pseudo language. And then when they increase the number of clusters, I think it makes sense. 25 seems to be too small for me. They compare these three numbers. Interesting. They raised the 3,000. They come from 3,000. Okay. I think this is strange. Because 1,000 was the best on the previous comparison, right? You should include the result of 1,000. Oh, because they have a dip here. They have a dip at 10,000 vocabulary size. They'll skip the results of 1,000. Okay, that makes sense to me. So, okay, they got 38.8, which is better than 41.7. Okay, then they further increased the number of clusters to 500, and they compare these three vocabulary sizes. And they found that 1,000 is the best. My guess is that the author, they found, okay, they go from, let me see, this is, say this is a 42, 41, 40, 39, 38. You can see this is the first best result for the cluster equal to 25. And this is the 38.8 is here. This is C equal to 100. And then when you go from, this is better, right? Yeah, they should draw a better figure. I'm doing this for them. You can see 500. I think I would say using log C. So 500 would also be roughly here. And they're only getting 38.1. So you can see they say, okay, this thing would like, it's like a plateau, flattened. So they're not gonna try more. But I would say it doesn't hurt to give a try of 1,000, right? And they only do the class, the pre-training on 960 hours, right? And then you got the best of the case is 500. But what if you increase this to 60K hours of speech? So what the C should be, more experiments should be done. And that they also compare the average pooling kernel size. I think this is trivial. Yeah, they use 2. That's fine. Optional average pooling. Yeah. I think it's when they are some averaging thing, right? Pre-processing, pre-training cost. Yeah, I think this is trivial. It doesn't change much to me. Okay, let me come to this conclusion the author made, okay? Yeah, I think they demonstrate the potential of the encoder-decoder model. They actually still only train the encoder, in my personal opinion, but they claim that they train the encoder model. But I think they're still falls into the category of encoder or pre-trained model. But definitely, I agree with them. Their encoder model reduce the amount of effort that's being needed to train the decoder. Okay. And it's beneficial to the CDC model. Wait a second. They probably have a decoder, but I haven't checked their code. And maybe I didn't read their paper thoroughly. Oh, you can see in the figure 1, they do have trained a decoder. You can see making sense. I think I missed the one thing. It's the second stage after the pre-training. Okay, after the pre-training, they need to do the fine-tuning. Fine-tuning, they have the transcription. Okay, right, and they are using. So when during the fine-tuning, the first using encoder and together with the decoder, they learned during the pre-training. Okay, you can see the blue one, the blue models, encoder and decoder are all learned during the pre-training. And when they're saying the previous pseudo language token, they means, okay, given the same audio input, okay, suppose I use the pre-trained model to run on top of the audio, I'm gonna get a pseudo language token sequence. Okay, this is they call the previous pseudo language token. Okay, and then they come up with also the ground truth. Replace during the fine tuning. Anyways, I think this is a little bit confusing to me. But I think that the point is, let me start from the beginning again. So they have to pre-train this encoder and decoder model. So during the fine tuning, they're again using the audio input to get a output embedding. Remember, the output embedding is not a pseudo language tokens, but it's a vector. For sure it's a vector. It's a contextual vector. Okay. So when they're calculating the loss, I think they're using the orange module saying that they're replacing something. I think this drawing is very confusing to me. They need to improve this. Maybe I didn't read their paper carefully, but I think the concept is that they are, so the decoder's output embedding together with the input embedding will be leveraged to minimize the loss. Okay, so they have this extra input other than the output embedding to help the decoder to be better fine-tuned. Okay. So originally the decoder, when you try to fine-tune the decoder is out, the input is only the contextual vector from the encoder, right? But I think now what they in their paper, maybe I'm wrong. Okay, this is my first thought after seeing this. They have this type of pseudo label generator, pseudo language generator module. So they, together with the CT, they also have a pseudo language token sequence input. Okay. Yeah, token sequence. So they have the extra information. And for learning, I think the ground truth should be the normal language token sequence or word piece sequence. So this is why I got confused when I saw this. Anyway, I'm gonna also go back to the conclusion. Yeah, I think they also mentioned something interesting they want to give a try to. They also wanted to try the pseudo subword to generate spoken language models. That's interesting. But I'm a little bit confused or not very clear about where the direction could be going, because you can train the pseudo language model on the pseudo subwords, but how do you anchor that model with the word piece model or the word models that's in our daily life? They also try say you could also add CTC laws to the encoder during fine tuning and do the joint CTC attention decoding. This is proposed by this stuff was proposed by Professor Watanabe-san. I think it's working very well. It could accelerate your training, or say your fine tuning needs less amount of data. Okay. They're talking about their limitations. Their model is purely end-to-end, no language models. I think it'd be interesting to see how their model works with when they plug in the external language model. No, so yeah, I got confused. All right, thanks for watching. See you next week.